Thanks so much for the nice introduction, and thanks a lot for having me. So today I'd like to talk about a topic that is not so much about specific models, but it's more about how do we make sure they're really working. So I'm pretty sure that we're all aware of these recent success stories of AI in healthcare. Um, you know, Stating that the AI is beating the doctors in their specific tasks. However, if we look closely, we will also find many press releases that are actually the other way around. So, stating the failures of all of these models. So, for example, the Google AI model that made up body parts, and nobody's noticing, or AI failing to detect critical health conditions, and many, many others. And if we think about those, we can ask ourselves, why is that happening? So we're working on AI for a few years now. So why do we still have these large failures? And I think one of the major reasons here is that we often, at least as AI developers, think of AI as the models. So what can we do to to add new building blocks to the network architecture? What can we do to make them even more efficient? Which is, of course, extremely important, but we often forget that there's also more about AI. It's not only about models, it's also about the data. How do we do the data set design? How do we ensure high quality annotations? How do we use proper metrics, or how do we compare algorithms to each other, and so on and so forth? So there are many, many things that are related to the validation of AI models that are as important as building models. And when we talk about validation, it's also what do we mean by that? So is it about trust? Is it about accuracy or an AUC score? Is it about precision, reliability, outperformance? So it's basically somehow a bit of all of them, but it's, for example, as seen here, um, if you have a model that has a score of, for example, 92% on a metric that doesn't really reflect what we care about, what have we learned? So we should always think about what do we want, and this is what do we do with validation. So validation is more than just testing. It's not only about a leaderboard score or a specific metric or like a final checkbox that we can take. Validation and evaluation is all about expression of values, also signal fitness for purpose. And it's also, we can see it like a bridge between the developers and the clinician in healthcare or anywhere where we want to deploy the model. And it's also, what we should not forget, it's a requirement for regulatory trust. So if we think of ourselves being on a road, like we see here, ideally we want to follow that road and go towards our real goal. So a clinical question that we want to answer. However, what we do in practice, we often diverge from that road, and we go towards an optimized goal. So we use, for example, if we talk about metrics, we use a proxy metric that we know very well, but we often do not really think about whether this metric reflects our real clinical question. However, this proxy metric is what guides clinical process. And we should always be aware about how we measure our algorithms to make sure that we're doing it correctly. And I would like to start, by telling you a bit about why choosing the most common metrics is not the best approach, although it may seem easy and others are doing it the same way. Let me start with an example. Brain tumor segmentation is a pretty common example for medical image analysis, and probably many of you know that. Here we see a data set that is pretty standard, and also an algorithm which is perceived state of the art. And what we see here is we have a reference from a doctor and we have a prediction from this algorithm. And if we compare those two on the brain tumor segmentation, so here in blue we see the segmentation, it looks good if we just compare it. And also, if we calculate the most common metric, the dice similarity coefficient, we get a 94% score, which is pretty good, right? However, from a clinical perspective, it's actually not so relevant to segment the very large tumors because they are pretty easy to identify. But what is much more interesting are the tiny lesions to give some information about progress of the cancer. So this is what we're actually looking for. And if we now look at the very same patient here, so the same MRI image, but a different slice, we will actually see that, oops, wrong direction, that this algorithm is not as good as we thought it to be because it's systematically missing the tiny lesions. But those are the ones that we're interested from a clinical perspective. So this metric that we have used is actually pretty misleading because this metric on a voxel level is not telling us anything about small structures. So we would need something like percentage of missed lesion or something along those lines to really have a metric that is, yeah, reflecting our clinical question. However, having this problem is actually not so, or solving this problem is not so straightforward because if we think about it, there are so many metrics out there, and each of these metrics have been designed for a specific purpose. So, for example, if we think of about sensitivity, specificity, these are metrics that exist for a very, very long time. But we also now use it for AI, and the question is, does it make sense? So each of these metrics have their pros and cons, and how should we be aware of all of them? It's pretty difficult. If we now go away from from healthcare for a bit and think about a different kind of event, so a sports event, a marathon, for example. I think here the metric is pretty straightforward. If we measure who would be the winner of the marathon, we would just take the time of everybody, and the one who is the fastest will be the winner, right? Or in other words, the one who is the first on the finish line. If I would now tell you to use not the time as a metric, but something like the shoe size of each runner, we would all say, okay, that doesn't make any sense. But that's somehow the way that we're doing it if we're using just any metric to assess the performance of algorithms. So we should really think about this metaphor when we think about validating AI algorithms. However, when we think of how people are actually choosing metrics, um, these are here examples from competitions where we have asked the organizers of the competitions to justify why they picked a specific metrics. And we very often see things like we see here. So this is a commonly used metric. This is the standard metric for this or that problem. It's a widely used metric in the field, indicating that we are typically using metrics because for their popularity and not really because they're clinically appropriate. And also, if we look at some numbers, this is also reflected. So what you see here in this graph is the frequency of how often a metric is used across different classification challenges. And here we definitely see that we have a lot of metrics that are only very rarely used. And the accuracy metric that we see on the top here is the metric that is the most commonly used in classification. And this is also for a reason because this metric is pretty common. It's easy to understand. Also for clinicians, you can very easily tell them what this metric is about. However, this metric comes with a very prominent pitfall, actually, in the presence of class imbalance. So let's think of an example. Let's say we want to classify whether patients have cancer or they have no cancer, so a binary classification task, and we have a pretty imbalanced data set. So something like this here, where we have lots of healthy cases and only a few rare cancer cases. So no matter what, we train an algorithm on that imbalanced data set, we test it, and we get an accuracy of 97%, which is a great score. However, if we look at what this algorithm is really doing, we will pretty quickly see that this algorithm is doing something pretty random because it's always saying that the patients are healthy, which is, of course, from a clinical standpoint, not useful at all. And we definitely wouldn't want to use something like that in clinical practice. But the problem is that accuracy is not designed to handle class imbalance. So it won't tell us a situation like this because just of its definition. And there are actually metrics out there that could compensate for class imbalance. For example, the balanced accuracy, which would, with a score of 50%, would tell us that there's definitely something going wrong here. But if we think about class imbalance, this is something that we very often see in clinical practice. So diseases often have a very low prevalence. So they, in reality, don't show up very often. So this is something that we definitely have to take care about. If we think of, again, brain tumor segmentation, here I brought you more algorithms and not the good one that we saw before, but some that are pretty weird when we want here in green to segment the tumor, and some of these shapes look pretty weird. And of course, I've made them up, but still, we would agree that not all of these predictions are very good for the problem at hand. However, if we use the most commonly used metric, the dissimilarity coefficient, this metric will tell us that all of these five predictions are of same quality, which, if we look at that, is definitely not the case. So the shapes of these tumors look really random. However, from a perspective of the definition of the metric, this doesn't care. So the metric is defined as the overlap between two structures. So if we would say here in blue we have the prediction, and in orange we have the reference, it will just tell us how much overlap there is between those two structures, and it doesn't really care where the overlap will happen. And if we have false positives or false negatives, where they are, it doesn't really care about. So this metric is only about overlap and not about shapes. But we should be aware of that when we pick our metrics. And I could continue like this for a while now. And we also have publications that have lots of pitfalls. And if you're interested, feel free to check it out. And also, especially the bottom one, which has a lot more. This is a dynamic preprint. So if you think we have missed some pitfalls that are interesting, let us know. We're always happy to include it, and also to have more co-authors on this paper. But it's always better if you not only raise awareness of problems, but if you also solve them. And this is what we did with our so-called Matrix Reloaded initiative. So perhaps some of you know the Matrix movies. There's where this comes from. But you see, there are many researchers involved, and we had one goal here, namely to define problem-aware metric recommendations. So this was a long process. We had more than 70 researchers involved, and we performed a so-called Delphi process. So for those of you not aware, let me briefly explain the concept. So we had a group of coordinators, and we worked on specific concepts of the framework. So for example, which metrics to include, and we put that into a survey. And the survey was then given to the Delphi expert panel. And as you see here again, we have many different institutions involved over the whole world. So we had different expertises in data science, in statistics, clinical expertise, biology, basically everything that you can think about that is somehow related to the problem. And with that, we could then iteratively integrate the feedback from the experts to make sure that we are deriving at a consensus decision on our recommendations. And we also got the feedback from all of these different expertises, which work on fields that are somehow similar, but also, every single application has their own specific insight. And it was really interesting experience to get all these different perspectives. So how does this framework look like? The main idea is that we're coming from what we call a driving biomedical problem. So the clinical question basically that we want to solve. So the problems that you see here on the top, where in the next step, the idea is that we're abstracting from that problem by a so-called problem fingerprint. And I will explain that in a second. So we're abstracting from that question by basically having a list of different properties, mostly binary questions where we say yes and no. And based on this list, and based on a specific pool of metric candidates, we could then decide which are the most suitable metrics for a specific problem. So we could weigh the pros and cons against each other. And as I said, the core concept here is the so-called problem fingerprint, which means we have different properties that are relevant for metric selection. For example, Are you particularly interested in this boundary of a structure? If we think again of the brain tumor segmentation with the shapes, here we would definitely say, yes, we're interested in the shape. Or do we have small structures? If we think about the problem with the missed lesions, this would be something where we would definitely have said, yes, we have small structures and we're definitely interested in having them. Do we have class imbalance? Think about the accuracy problem. So you see, we chose these properties according to the pitfalls that we have identified, and there are lots of more in this list. And given that, we could then make sure that we're suggesting metrics that are not falling into these pitfalls, but that are compensating them, that are making sure that we don't have these problems. And this way, we could abstract from the problem at hand and could generalize across domains. So it's not really important what kind of problem we have. So let's look into the framework, which is at a first sight looks a bit chaotic and many arrows, but it's actually not as bad. So let me guide you through it. So as I said, we start with the fingerprinting problem. That means we're going through that list of the properties that I've showed you, and we're answering it for the problem that we have at hand. And based on this, we now have that checklist that we can use to decide which metrics are the best ones, which brings us to the metric selection panel. And this is a very big panel, and you see there's a lot going on here. But actually, if you think about it, we have different colors of these arrows. And these arrows indicate different types of problems. So, for example, an image level classification or semantic segmentation. And if we just focus on one of them, say the semantic segmentation, the whole thing directly looks much easier. So let's follow that branch here. So let's say we have generated our problem fingerprint. We follow the yellow branch for the semantic segmentation. Let's say we're doing a liver segmentation. Then it says we should first select an overlap-based metric. Then we have here a bunch of candidate metrics. And we have this plus symbol, which means we're going into another decision tree. So let's do that. This decision tree will in the end bring us to an overlap-based metric. An overlap-based metric is similar to the DICE metric that we've seen before, a metric that measures how much overlap do I have between prediction and reference. So we are following that branch here. For example, so we should first check what type of problem we have. Either do we have an instance segmentation or semantic segmentation. There are some exclusion criteria. And then we have specific boxes here which reflect the questions from the problem fingerprint. So for example, this one asks me if I'm exclusively interested in the center line of structures. So this could be interesting for structures like vessel trees or airways. So something that is very thin and has very like many different paths. If we think about that liver segmentation, we have a very large structure, so this would not be something where we're interested in. So we say no. And we come to the next question. In this case, it asks, do we have an unequal severity of class confusions? Which basically just means are over or under segmentation equally important? So for example, for radiotherapy, it would be very important that we definitely hit all of the sick tissue, whereas in other applications, we wouldn't want to damage healthy tissue. So again, it depends on your problem. Sometimes it's also of equal importance. And then, for example, if we say it's an equal handling, then we would end up here in the node, which is telling, okay, there are two metric candidates that are very good fits, but you should use a decision guide to decide which metric is best. And the idea behind a decision guide was basically that we couldn't really reflect every single potential problem that is out there. So we basically boiled it down to the most, to the best candidates and then leave the final decision to the user. And in this case, it was a decision between dissimilarity coefficient and intersection over union. If you know them, you perhaps also know that they're pretty much identical. So you could directly compute one by the other, as you see from these formulas here. So it's more or less a question of which community preference you have. So for medical, it's mostly dice. For computer vision, it's mostly IOU. But you shouldn't use both and just decide on your preference here. If you've done that, you have selected an overlap-based metric, and then you go back to the main decision tree, which will in the next step tell us that we should select a boundary-based metric. So a metric that can reflect the shapes of the object. So if you remember, we had the problem that the dice metric has a problem in reflecting, how good we are or how accurate are our shapes. So if we use a boundary-based metric, this can basically tell us, okay, my boundary is accurate or not. So we would do the same thing. We would again go to another decision tree and pick one of those candidates that we have over here. And one of the important things that we're recommending here is that we're not using a single metric to assess performance, but using multiple metrics. But there is not this one single metric that can tell you everything about your algorithm. You typically have multiple things that you're interested in, and therefore you should have multiple metrics reflecting those goals. And also, for example, we're giving so it's not like a very, very strict framework, but we're also giving people the opportunity to select application-specific metrics. So metrics that are very specific to your use case, to your specific application. So if we stick with that liver segmentation example, this could be something like the volume of the liver, because this is something that clinicians are typically interested in. We could also select non-reference based metrics, so a metric that is not comparing a reference image to a prediction image. For example, something like the runtime of the algorithm, which is important for real-time use, or the carbon footprint, or anything in these directions. And similarly, these ideas also hold for the other image tasks that we have, so classification and detection, or instant segmentation as well, and you would do the exact same procedure here. Yeah, and finally, we're giving some recommendations on how to apply those metrics. So for example, for classification tasks, how do I best determine a global decision threshold, or how do I report those metrics? So this would be the general idea of the framework, but as you've seen, it's quite a lot. So there are many different questions that you have to answer. You have the different decision trees. So we've tried to make it, very or much more accessible to the users. And this is why we had different measures to make it more user-friendly. So one of the things is that we've asked the community, what are the use cases for which you would like to see a recommendation? And then together with our experts, we worked on the problem fingerprint, and we have come up with a different recommendations. So you see a few examples here on the right, but we also have more in the supplements of the paper. So for example, say you have down here an instant segmentation of neurons from the fruit fly and 3D multicolor light microscopy, which is of course a very specific problem, but still you can directly see the recommendations that we give for this very specific problem. Another thing that we have did, or something that we have noticed when we talked about metrics, it's very difficult to find all relevant information for one metric when you search for it. Because there's some information maybe in this article, in this paper you find something else. But so you basically have to find everything on your own. And we wanted to do something against that, so we created cheat sheets for every metric. So for each of the metric, we have compiled all the relevant information in one single sheet, where you find things like the formula, a short description, but also important relations to other metrics, multi-class definitions, relevant pitfalls and recommendations, so that we have all of the important information for one metric at one place. And from experience, people tend to forget things, including myself. So it's really quite nice to have something like this available. Another thing that we have came across with, and also an important pitfall, is that it depends on which libraries you use when you implement a metric. So perhaps not for the very, let's say, easy formulas like accuracy, but there are always edge cases. And for some more difficult metrics, like, for example, average precision in detection tasks, it makes a difference which implementation you use. And without going into too much detail, you just see here two examples where different implementations of the same metric for the same use case will give you very different results So this makes a big difference also if you report your problem, right? So we've also sat together and implemented the metrics in a way that we think is most accurate. And you find that here in the Monai framework. If you don't know Monai or don't use it, it's actually not important. It's just under that umbrella, so you don't have to use Monai. It's just yeah under the same thing, but you can just use it independently if you want to use that. There are also examples and tutorials, so if you want to try it out, give it a go. Yeah, and finally, for this metric project, we wanted to make it yeah as easy as possible. So we have also implemented an online toolkit where you don't have to worry about all of this theory and where you find all of the different things available. So this toolkit guides you through all of the relevant steps. It gives you explanations. And here, for example, we're starting the semantic segmentation process again. It asks you all the relevant questions from the problem fingerprint. So you also have yeah, an illustration of what we mean by the question. We have some more text and also note where you want to, if you want to read this further. And then you're just answering these questions. And from time to time, you will see some metric recommendations popping up. So you're just guided through the process. You don't have to worry about anything. And in the end, you will also get a full report of what you've answered if you want to discuss something, for example, with a clinician. And you also have some insights, for example, in the metric library, you will find all of the different cheat sheets of the metrics. So I also highly recommend checking this out. Makes your lives pretty easy if you're unsure about which metrics are the best. So let's now assume that we have selected a proper metric. The next question is now, how do we apply such a metric? So let's talk about rankings. Rankings, it's not only about in a competition, but also if you're performing algorithm benchmarking. So rankings basically determine who's the best method. But it's not so straightforward actually if we think about it. So let's say we have a bunch of different algorithms. So let's say you're this algorithm and you're comparing yourself among different baselines, but you have different images, and for each image you have one score, or perhaps even multiple scores. So the question is, what do you do? So there are different ways. The most common one I would say is for each algorithm, you just aggregate all the values that you have into for example, a mean score or a median or a percentile. But there are also different ways that you could do it. You could also, per image, create a ranking and then aggregate the ranks across the algorithms with a mean or median or whatever. Or you could try other things. I've seen multiple things that you could do. So, for example, you could also calculate how often am I statistically significant to the others, and then use this number. So there are various different ways that you can do it. But I think the main idea is it shouldn't matter. So if I'm, let's say, the winner, I should always be the best method, independent on whether I do it this way or that way, if I use mean or median. And this is what we wanted to have a look at. So we investigated ranking robustness, and luckily we had all the data from all participants from the MICAI 2015 segmentation challenges. So we had a lot of data that we could work with. And we found that the rankings are actually very, very sensitive to a bunch of different parameters. So on the one hand, which metric do you use? How do you aggregate? And all, even who annotated the data made a difference in the rankings. So let me show you a few examples here. So this is one of the real challenges. So we had 13 participants, and this is the ranking that you get if you aggregate with the mean for algorithm 1 to algorithm 13. But if we think about it, using the median shouldn't change that much. However, what we found here in this example, algorithm 1, so the winner is suddenly at place 5, and place 5 is now at rank 1. So yeah, basically changing the ranking a lot. And this is even more apparent if we try different things. So for this experiment, we have a different challenge here. We calculated the default ranking scheme, so the one that was used in the challenge, and we compared it to 11 other ranking schemes. So for example, we changed the metrics, we changed the aggregation operator, and we changed if we, for example, first aggregate over the algorithms, or if we first rank for each image and then aggregate. And we see is that the rankings change completely. So I've highlighted a few in colors here. If we follow the first one here, we'll see that it's pretty stable for the first four ranking schemes, but then suddenly it drops down to the very end of the leaderboard. And someone from the middle is now at the top. Someone from the bottom is also pretty good. So you basically see you shouldn't really trust those rankings. But the question is, okay, what should we do? When we cannot trust the ranking, yeah, are we lost, or what's the best way here? And one of the answers is also similar to the metrics. Think about what you want to show. So what is your clinical question? I've once organized a challenge, and we wanted to know basically the robustness. We wanted to know if algorithms also work in the worst case scenario. So what is the worst case performance? And therefore we have used a pretty low percentile, so the fifth percentile instead of a mean, for example, for aggregation. But there's definitely other things that make your life easier. And one thing is results visualization. Sounds pretty simple, but it makes a big difference. So we have an example here. We have 5 algorithms each, and we have box plots for each of these algorithms. And we also show here the individual metric scores as dots. And if we look at the top example here, I think it's pretty obvious if we would calculate a ranking. Yeah, we directly see it here, right? So this algorithm is definitely better than the second, and this one is better than the third, etc. On the bottom, we have another example, so also 5 algorithms and the box plots. But here the situation is pretty different because all of these are looking somehow similar. So it's not so easy to find out which one is really the best. So for example, here for the first one, the median looks a bit higher than for this one, for example. But yeah, they have a different distribution. So which one should we take? So independent on what we do, both of these situations would yield the exact same ranking table. And why is this a problem? Because in many, many publications, we only see this. We only see the ranking table, and this tells us nothing about how close are the algorithms together. Do we have a clear or an unclear situation? And sometimes we don't even get a mean value. So it's definitely a very, very important step to already use something like box plots to show the performance distribution of the different algorithms to see also what is our standard deviation, etc. But there's more that you can do. So let's talk about bootstrapping. You can use bootstrapping to assess ranking uncertainty. And with bootstrapping in this situation, I mean that we want to simulate small perturbations of my data set. So basically what happens to my ranking if I have a slightly different data set than before. And just as a recap, how does this work? We start with our data set, and then we do resampling with replacement. So from this data set, we pull different images out, and we create a new bootstrap data set. For example, we have the blue cases twice here, and we're missing a few others. So we have a slightly different data set, and then we calculate the ranking again. And we repeat that, for example, 1,000 times, so that we get an insight or a distribution of what happens if we have these small changes in our data set. And this can be used to assess the uncertainty of the rankings. So if we go back to this example here, we could use these bootstrap examples and plot them in what we call blob plots here. So here you see the algorithms against the individual ranks. So, and the radius of these blobs indicate how well or how often an algorithm achieves a specific rank. So in this clear example, every algorithm is, so for example, the first algorithm is always on rank 1, the second is always on rank 2, the third always on rank 3, etc. And for the bottom example, for the unclear ranking, every algorithm achieves every rank at some point throughout these bootstrap samples. So this is definitely not a very clear ranking, and this is a situation where I shouldn't directly say that we have a winner or a method that is clearly outperforming the others. And we have implemented also a toolkit for this, where you just insert a table of CSV, a CSV table with all of the different values of the metric scores, and then you get a full PDF report out there with different ways on visualizing and analyzing ranking results. So I've just showed you one, but there are many, many more that you can try, and it's also something that I would recommend trying out, not only for benchmarking experiments, but you could also use it, for example, for hyperparameter tuning. But talking about rankings and presenting results, I've briefly touched upon outperformance claims. Um, so I showed you that we often see these tables here. So we compare our methods to different baseline methods. We hopefully get at least a point estimate of some metrics, but that's often it. And we've already seen the consequences of not visualizing our data. And this is also something that is criticized by the FDA, for example, which mentioned that statistical analysis is very important and very crucial when we assess machine learning performance. And they're criticizing that there are still many publications that only present these point estimates that you see here. And we wanted to know if that's really the case or if it's just our perception. So we have analyzed more than 200 papers, and we wanted to know basically, do they report variability? And you can see here from this plot that in more than half of the papers, they didn't report variability. And for those who did, it was not much better actually, because there was only one single paper that reported a confidence interval, and some of them that reported something like standard deviation, but in many cases we were not sure because they were just saying a mean value plus minus another value without specifying that this plus minus value is a standard deviation, could also be standard error, for example. But this distinction is important to know what we're talking about. And also the way how standard deviation was calculated was often not clear. So was it over an independent test set? Was it from cross-validation or something else? So we definitely have a reporting problem here. But coming back to the question of outperformance claims, so we wanted to know what is the delta in metric score between the proposed method, so let's say the winner, and the competitor. And we have analyzed it over all these these 200 papers, and the median improvement in the DICE score, so the most common metric, was 1% point, which is definitely not a lot. And the question is, can we really say that we are outperforming someone else with just 1% improvement? However, more than 80% of the papers claim that they are outperforming the state of the art. So let's say we have this median improvement of 1% point. If we have a confidence interval, the confidence interval is basically telling us how confident am I with my mean estimate. So the confidence interval should be smaller than this delta in the DICE score. However, we found in practice that the reality was that the median confidence interval width was 3 times as large as this median improvement. And by the way, we also found exactly the same numbers for accuracy. So this is also the case in classification. So this really raises the question, can we really say that we are outperforming others? And without going into too much detail, we investigated this. We have derived a formula to calculate the percentage, the probability of false outperformance claims. And the results are actually what we have expected. We have a very high probability of false outperformance claims in more than 80% of classification and more than 50% of segmentation papers. And this is also what you see here in the plots. Here you see the test set size versus the difference in the metric scores, and basically orange means bad. So everywhere we have orange, this means that we have a very high probability of false outperformance claims. And this is definitely something, that is somehow disturbing. So to keep this in mind, it's always important. Of course, this is somehow the practice that we learn when we publish, right? So journals want clear messages, they want new methods, they want us to tell everyone that we're better. But the question is if we should really do that, and I'm questioning a bit the practice that we're doing. So be careful when you do that. report the variability, make sure that you're using the metrics in a good way. And as you see here from the top plots, the larger the data set, the better for this situation. So there are many more things that I could talk about, but these were just a few things that I think are important. And if we think again about this road that we've seen before, if we try to do all these things, of course we will not be perfect, but if we try to think about it next time, that we're using a metric that is better, that we are using a reporting in a way that is better, then we're slowly getting towards our real goal instead of only optimizing in the wrong direction. So exactly, this is the road that we want to take. And with it, I would like to thank you so much for your attention and happy to take questions.
All right. Thank you so much, Dr. Reinke. That was quite insightful. Okay. So we're going to open the floor for questions. Um, if you have questions, you can leave them in the chat or use the Q&A function. But I've been curious um, about what is your personal failure in practice that must change on how we evaluate models today?
Yeah, that's a good question. So I think, um, as I said in the beginning, I think we're very much focusing on models solely, and I think we should independent on what topic it is it metrics or rankings or data. I think it's very important that we always talk to the people where we are doing our methods for example, clinicians. And I think this is something that, yeah, it should definitely be something that we should keep in mind. So we should always know what is our real goal, and we should always try to make it the best way possible. It's not straightforward, definitely, but I think this is the best way that we can do it.
Hmm. Oh, thank you so much. From your statement, I can deduce that it will be good for us to co-create with the end users of this model, the clinicians that
Yeah.
would actually be using these models to um, perform diagnosis. That's quite very important. Um, Thank you so much for that answer. And also, if you don't mind, what will be the minimum evidence you will want to see before letting a model touch a real patient? Will it be external validation, some calibration, or what kind of evidence in terms of metrics or evaluation would you like to see before any model reaches the patient?
Yeah, good question. Um, so I think so something it depends. I think it should always depend on the context, and this is also something that is somewhat hidden in these metric
Mhm.
recommendation frameworks. I think it's very important that we contextualize our values. So on the one hand, we should pick a metric that is relevant for our situation, but we should also make sure that this value makes sense. So just having a score of 90 something percent doesn't
Mm.
always mean it's good. We should compare it, for example, to human baselines. So how
See,
well are the humans? If the humans are at 80% and we're at 90 with the algorithms, that's great. If the humans are at 90 and we're at 70, we shouldn't do that. So I think that's the minimum thing that we should always do. So to think about what is the context.
yeah, yeah, I totally agree. I think we
Sorry,
have a
could I
question.
ask a question? Oh, sure.
All right, yeah, okay, sure. Juan Pablo, you can go ahead. Please leave
Oh,
your
sure.
questions in the chat. They can use the Q&A function as well as the chat. Juan Pablo, please go ahead.
Oh, sure.
Mm.
Thank you so much for the great talk. Um, I had a question regarding the metrics reloaded, where you guys went through and analyzed like which metric was best for each kind of scenario. And you said that there is like this concept of like the most common metric that people often report, and that's sort of what they go by. I'm curious in your analysis. were there some cases where you found that the most common metric sometimes wasn't the best one, or was it usually the case that the most common metric sort of had some pretty good like reasoning and backing behind it?
Yeah, interesting question. I need to think about it. But I think mm, again, the answer is always depends. There were situations where I think it was fine. For example, the dice metric is always by far the most commonly used metric because segmentation is just one of the tasks that we most often do. And it's not per se a bad metric. It's just a bad metric if you use it as a standalone metric. But if there are situations where you combine it with, for example, Hausdorff distance or normalized surface distance, depends on the use case, of course, but then it's fine. But in most cases, I would say that it's not always the best choice to just do what others are doing. Also, we found interesting insights where, for example, people have used a metric that was introduced in some paper, which actually had an error in it. And people didn't really question it. They just used that formula all the way. So this wrong practice propagated across the way. And I think these are the things where we need to be careful about.
Thank you so much. We have another question here in the before I proceed, Juan Pablo, do you have a follow-up questions?
No, I don't. Thank you so much.
All right. Thank you so much. We have a question here in the chat from Oyetun J. It says, in your expert opinion, which metric do you think is more of clinically oriented rather than statistically oriented?
That's a tricky one. And I think I cannot answer this definitely because this always depends quite a lot on the clinical question. So the thing that I've learned from when talking to clinicians, most of our technical metrics are not relevant. Um, I've showed you this example with the liver segmentation. We are doing complex things like the overlap and the boundaries, but clinicians often are only interested in the volume. Um, but I think this is also something where we need to think about. So on the one hand, we need these technical metrics to assess our algorithm from very different perspectives. On the other hand, we also need to talk to clinicians to establish something like that. And I think there are just not yet the clinical metrics that we actually need. I think we're not yet there. I've just recently talked to clinicians about potentially, making this better and establish these metrics. But I think at the current stage, we are not yet there.
True. Thank you so much. You touched a little bit on the concept of noise in evaluation when you talk about inter-rater variability, and I had this thought of how can our evaluation metrics actually adapt to this kind of noise? Do we need to have some other boundary tolerant metrics or have some soft labels that guide the evaluation problem? Because that is actually a problem that have not really been given much attention over time.
Yeah, you're right. And so I know a few metrics that actually have these tolerance values. For example, if you're interested in a boundary that where you can set a parameter of what is basically your iterator variability, I don't know, 1 pixel, 2 pixels, um, but not for every single problem. I also know that from surgical things, but definitely something like soft labels is something that I think we should have a look at. I know that this is on my to-do list also for a while now, but also not yet there. So there are a few metrics, but not all of them are perfect, I would
I
say.
see. Okay. Thank you so much for that response. We'll be looking forward to what you will be having in mind or toolkits that can accommodate that. Yeah, we'll have a question here that it says, what advice will you give to researchers developing AI models in regions where collaboration between AI developers and clinical practitioners are limited?
Mhm. Yeah, that's of course something that we often face, right? Not everyone has access to clinicians. So in that case, I would try that metrics reloaded tool, and think about it from your own perspective. Do some research about your problem. I mean, if we're doing a PhD, we typically have some kind of application that we're working on, for example, right? So yeah, try to read as much as you can to get an overview of what is important in your field, and perhaps also give it a try and try to look into the clinical perspectives a bit more rather than the technical ones.
Yeah, true. Yeah, thank you so much. I don't see any questions. I will just ask maybe this last question before we call it a day. We have just 3 minutes more. Like in conclusion, what will be a model agnostic path to clinical translation? What would it look like if we centered evaluation over architecture and models? What would be a model agnostic path towards clinical translation?
Yeah, that's a good one. Um, so I think we need to identify all the let's say dimensions that are important. Um, the data needs to be presented or prepared in a meaningful way. We need to make sure, for example, that we're not falling into data leakage problems. We need to make sure that we have the right metrics um, for validation. We need to make sure that we have an untouched test set. We need to make sure that we are presenting the results with uncertainty, etc., and have a contextualize them. So the things that I've touched upon, and I think in that way we're going towards that path. Something that we're working on. I know that it's quite a lot, and I know that it will take us quite some time to get there, but this is the ideal vision that I would have in this regard.
Okay. Thank you so much. Oh, there is one more question here as I'm planning to wrap up. It says, is it possible we have access to the slides? As we have access to the slide or materials? I think they're requesting
Sure.
for a slide. If possible, we can share with the community. Yeah.
Yeah, sure.
Thank you so much. Great presentation. Thank you. It's been one
Thank
hour
you.
of a lot of information and knowledge that we need to try. And to our audience, I would say, if an idea has been sparked today in your mind in terms of evaluation, I have been dropping the papers and the toolkits in the chat. Please try the problem aware metrics. Check out the checklist on your next project, and feel free to let us know if you have any other questions, or you can reach out to Dr. Hienke directly. Thank you so much, Doc, for this session. It's been wonderful, and you made it more wonderful this time around. Thank you so much. Glad to have you.
Thank
I
you for having me.
think we're going to call it a day here in the absence of any other questions. Thank you so much to the organizers and the chairs, Juan Pablo and Dr. Maruf. Thank you so much. And to our attendees, we're looking forward to seeing you all again next month for a great edition. Thank you so much and have a wonderful weekend. Yeah.
You too.
All right.
Bye bye.
Bye. Yeah. Bye, everyone.